Laura was born on 29 of October 1711. In 1732, she earned the degree of Doctor in Philosophy from the University of Bologna. A few months later, because of her remarkable scientific skills, the Senate of the University assigned her an honorary position at the chair of Philosophia Universa, that is, of natural philosophy. In the following years, the young woman continued to study. In 1738 she married Giuseppe Verratti, a doctor in medicine who shared with his wife a keen interest in the study of nature. In 1745 Pope Benedict XIII admitted Laura Bassi among the elite group of scholars named Benedictine academics, but only as a supernumerary, and not without resistance. Filling this role, she had to present at least one original dissertation a year. In this way, Laura played an active role inside the Bolognese scientific community. For performing her talks, Laura carried out several experiments with her husband in her own home, in a special laboratory that the couple had equipped with the most advanced tools and machines of the time. This laboratory was used not only for her personal research, but also for the private lessons in experimental physics that Laura Bassi held for philosophy and medical students of the university. The almost 30 years of high-level lessons held by Laura at her home earned her the assignment of the position, this time effective, of Professor of Experimental Physics in the Institute of Sciences in 1776. Only 2 years later, on the morning of February 20, 1778, Laura Bassi died suddenly, after having participated in a session of the Academy of Sciences the previous evening. This woman, a forerunner of female emancipation, remains an admirable example for all women of science still today.
Okay, so it is my pleasure today to introduce you our speaker. She is Eleonora Alei. She's a postdoctoral researcher at the ETH Zurich, where she is currently leading the atmospheric modeling team, which is focused on defining the technical requirement of the life concept, a space mission that may help find life in the universe. She obtained her PhD in astronomy at the Astronomical Observatory of Padua, here in Italy, on atmospheric modeling, and also have worked with biologists and engineers to build an experiment setup to simulate exotic atmosphere in the laboratory. So without any further delay, I pass the baton to Eleonora, who will tell us today about life in the universe and everything.
Thank you very much. I'm quickly sharing my screen. Right, can you see it?
Yeah, go ahead.
Cool. All right, so thank you for having me here. It's a real pleasure to be part of this series. As Nancy knows, I really wanted that. And yeah, today we will try to talk a little bit about what I do in the context of LIFE, the Large Interferometer for Exoplanets. And as you see from the title, there's going to be also a little bit of a few pop references throughout the talk. Starting with this one, obviously, this is an obvious reference to my favorite book, The Hitchhiker's Guide to the Galaxy by Douglas Adams. We will talk a little bit about the exoplanetology and the latest, what we know so far about exoplanets so far at this point in time. And then we will start narrowing our discussion more towards the the quest for another Earth, the Earth twin in the universe, and how are we working towards that goal? All right. So we should start by defining what an exoplanet is, or extrasolar planets. These are planets that orbit other stars other than our sun in our galaxy. And it's impressive how much progress has been done concerning exoplanets, considering that the first exoplanet was orbiting in a main sequence star was discovered not even 30 years ago. And this is the amount of planets that we know so far. Last time I checked, we know about 5,000 confirmed exoplanets, even more, around 8,000 if we include the candidates. And we see from this graph that I'm showing here, the mass versus the period of the planet, we see that there are different classes of planets. Some of them are also very interesting because they are not present in our solar system, as we will see later on. We can also notice that other than spanning a super wide range of masses and periods, we also have different methods that are more or less effective in discovering exoplanets. And we will quickly run through the main ones. The first one is the transit method, which basically measures the dimming of the light of the star that is caused by the transit of a planet in front of it. This is what happens if we observe, for instance, Mercury or Venus crossing the disk of the sun. So when we observe a star, we observe a periodical dimming of the luminosity of the star, and by observing it long enough, we can infer the presence of a planet that way. So in this case, we are not seeing any direct measurement of the planet itself, but we see the impact that the planet has on the star to some extent. We'll see later. What we can do with this technique is we can get a measurement of the radius, especially if we know the radius of the star. We also get, obviously, a measure of the period of the planet, so how long it takes to make a full orbit around its star. We also have some idea about the inclination of the orbit. And again, if we look closely by doing spectroscopy, as we will see, we get also a few information about the atmosphere of the planet. This technique is sensitive, obviously, to larger planets, because the larger the radius, the more light is hidden from the star, so it's easier to detect them. And also to close-in planets, because they are much more probable, much more likely to transit. And missions that have used this transiting technique have been very, very popular, because they allowed us to get a lot of new candidates. And most notably, we can mention Kepler. And right now, TESS is doing the great work. And in the future, also Plato will contribute to this. The second technique is the radial velocity, where we, again, don't see the planet directly, but we see the effect that the planet has on the star. In this case, the effect is the wobble of the star, because it's clear that it's not really the planet that orbits the star, but rather both star and planet orbit both around the center of mass of the star planet system. So the star also orbits around this center of mass. And we can observe this wobble if we notice a blue shift or a red shift of the lines in the spectrum of a star. This technique is, again, very sensitive to massive planets, because they cause a larger wobble on the star. And thanks to this technique, we can have an idea on the minimum mass of the planet, the period, the eccentricity. Now, if we manage to detect planets with both the radial velocity technique and the transit technique, we get many, many data about these planets. So we can start doing some statistics about it. But what would be what's the best way, if possible, to detect a planet, if not taking a picture of the planet itself? This is done through the direct imaging. And again, this is just taking a picture of the planet. We detect at this point the true signal of the planet rather than the signal that the planet creates on the star. This comes with a few technical challenges because the luminosity of the star is much, much larger. So we need to find a way to hide or block the light of the star in order to be able to see the planet. But we managed to do that in some cases, like just like this system here, or for hot Jupiters. This technique is sensitive to planets that are farther away from the star, rather than the other two techniques more focused on the close-in planets. And also we are more sensitive to hot and young planets. From this technique, we can retrieve some information about the radius and the mass. Now, granted, this is somewhat dependent from the models that we use to do so, but we can also get some intel about the atmospheric composition. And this could be interesting when it comes to defining how a planet is, what is the atmosphere of a planet made of, especially in the context of habitability, as we will see in the next few slides. Right, coming back to this plot here, I show here the position that Jupiter and the Earth would have in this plane, the mass period plane. And as we see here, we see planets that are fairly different from what we know. And in particular, we can divide them into different classes. We have the gas giants, so planets that are more or less like our Jupiter, but even more massive, up to nearly 10 times the mass of Jupiter. And then we have the Neptune-like planets that look like Neptune, but not necessarily in terms of composition. Then we have a class of planets that's not present in our solar system, which is the super-Earths, which is also very interesting because they seem pretty popular, and they are basically rocky planet with the mass up to 10 times the mass of our Earth. So we don't have anything like that looks like that in our solar system. So that's pretty interesting, if you tell me. And this is something that the community is more and more focusing on. Finally, we have planets that are, at least in terms of mass, more like the Earth, so terrestrial planets, likely to be rocky, but also could be lava worlds, for instance. And as you see here, from this graph, we see that there is a lot of gas giants that orbit, in most cases, very close to the star. They have orbits of the order of days, and so they make a full orbit in tens of days, up to 100 days. And this is something that we also don't have. These are called hot Jupiters, and this is also something that has blown the mind of the astronomers up to this point. What we also see is that there are not a lot of planets that look like our Earth, or at distances and dimensions that are similar to the one that the Earth has. So why is that? Is that because there is just one Earth in the whole universe, and so we're just lucky to be in the only planet that looks like this? I'm not so sure about that. I would rather say that the techniques that we have so far are heavily biased towards close-in and large planets, as we've seen here with the blob of the transits and the radial velocity. So we will be able eventually to detect planets that look like our Earth. We just need to be better at it. We need to improve our technology to be able to do so. And as I was mentioning earlier, the temperature is also something that's very different. in the sample of exoplanets with respect to the solar system. We see this class of very hot Jovian planets that we don't have in our solar system. And that would likely mean that those kind of planets have a very different atmosphere compared to the Jovian planets that we know more about. So this is also very interesting. We would like to know better how these atmospheres, the atmospheres of such planets, how these look like. So we need to start thinking about how we identify the main features of the atmosphere of a planet. And we do that using spectroscopy. And this can be done either when the planet is transiting or is about to go behind the star in the so-called secondary eclipse, because we see the interaction of the light coming from the star that interacts with the atmosphere of the planet. And from that, we can see in the spectrum absorption bands that belong to the atmosphere of the planet. From that point of view, we can understand how, to some extent, how the atmosphere of what the atmosphere of a planet is made of. And there are also other things that we can understand from this. In this picture here from Singh et al. 2016, which is very, very famous in this field, we see the data acquired from HST and Spitzer of several hot Jupiters. You will see the dots in this case, compared to the theoretical spectra that models have produced for these planets. And we see that by studying the spectrum, we get information about the abundance, well, whether there is a particular element in the atmosphere or molecule in the atmosphere and how much, so its abundance. We also have information about the atmospheric dynamics, the thermal structure of the atmosphere, and if there are clouds, in this case, like these planets here, they tend to mask, at least in the visible, the majority of the spectral features. So clouds can be interesting to study, but also very challenging. And all of this is progress that we've made so far with the current technologies. And there are a few missions that are going to improve the characterization of known exoplanets. And one of them is worth mentioning is Ariel, is a mission that will focus on the characterization of atmospheric characterization of known exoplanets. But also JWST and Cheops will play a massive role in this. So at this point, given everything that we have so far, we need to start thinking about what's next. And arguably, one of the next milestones will be to look for another Earth, to start looking for habitable planets. So at this point in the discussion, we will have to make a definition, or well, try to attempt to make a definition for this. It's not easy because as we will see, the concept of habitability and life is fairly complicated even to define. But let's say for now that the habitability of a planet is the ability of this environment to support and sustain life. What do we mean by life? This is also another complex point. And for now, for the sake of, in a way, maybe simplicity, we refer to life more in a terrestrial sense, because the life on Earth is the only kind of life we know so far. So it's the only data point we have. So it's much easier to look for life that looks exactly like the one that we know about, because we know how to look for it. We know we can characterize our own kind of life. This doesn't mean, of course, that there could be other forms of life. But for now, and for the remainder of this talk, we will say that life is in a terrestrial sense. That means that we are talking about carbon-based life forms that survive under using liquid water as a solvent and under temperate situation, environments. The first thing that we can do to define the habitability of a planet would be to define the habitable zone. The habitable zone is defined as the area around the star where that would in principle allow the presence of liquid water on the surface of a planet, of a rocky planet. This is a little bit more specific in this case. The habitable zone was actually defined in terms of a sun-like star orbiting and an Earth-like planet orbiting it. So it's very Earth-centric in this case. We define this area depending on the radiation that we get from the star. And it goes without saying that different stars, different dimensions of stars would translate into farther out or close in habitable zones. In particular, for hotter stars, we would see a habitable zone that's farther away from the star, while cooler stars would basically shrink their habitable zone towards shorter distances. Now, it's obviously not enough to have a planet in the habitable zone for it to be really habitable or inhabited, because the habitable zone is just a rough order of magnitude idea. Any rocky exoplanets could also not be habitable because so many other processes appear in the definition of habitability. And this is what we'll see here. This is the lovingly called planets are hard infographics that shows all of the processes that play a role to some extent in the definition of habitability. I can mention a few. Since we were speaking of the star, the age of the star can be a problem because large stars also have shorter lifespan, and life could not develop in around stars that are that big. At the same time, the magnetic field and the activity of the star or the stellar wind, which is particularly strong in smaller stars like the M dwarfs, could potentially harm the habitability, and they could threaten the survival of life on the surface of a planet. Other processes that are relevant are the presence of other planets in the system, like, for instance, Jovian planets, or, and most importantly, the planet itself that can play a role in this, because the planet is a very, very complicated being. I like to call it a complex sphere. That's because we are dealing with various spheres, as we see in this picture here. There is the atmosphere, the cryosphere, the biosphere, geosphere, and the hydrosphere, which means that the atmosphere, as we have probably surely studied in school, we know that there is a relationship between the ocean and the atmosphere, for instance, the water cycle. There is also a carbon silicate feedback that can also contribute to the weathering and to the interaction between the geosphere, the hydrosphere, and the atmosphere. And life itself, the biosphere here, life has caused massive variations in the atmosphere of our Earth, as we will see later. So it's really, really complicated to define habitability and life in this sense. So this doesn't really, the only way that we can do it properly is by talking to other experts. So we need to start creating a common jargon between biology, chemistry, astrophysics, and geology, and they all need to work together to define life. And because all of these branches of science have contributed in some way to life on our Earth. So we would expect the same orbiting around other stars on exoplanets. Okay, big break. Right, but what can we do as astronomers? What we can do, and as I showed you earlier, is to study the spectrum of a star, of a planet. And that's up to now the only way we have, the only window we have on a planet, because we cannot really travel on an exoplanet and send a probe and get in situ measurements or take pictures of the tiny little aliens that are on the surface, if there are. This is something we cannot do. We only have access to the, the atmosphere. And in this case, we can define the so-called biosignatures. That means signatures in the spectrum of an exoplanet that could be byproducts of life. In this figure here, I showed a few qualitative spectra of Venus, the Earth, and Mars. We see some similarities in some of them, in all of them, but there are also a few differences. And you know, in case you didn't know, this is the only one that we know has life so far. Let's think about Mars in another talk maybe. So what we see is that all of these planets have a band of CO2, but the Earth also has a spectral feature of O3 and water. So one might think that these two could be some sort of in some way indicative of the presence of life. Now with water, we need to be careful because water is also present in other planets that don't necessarily have life, but the detection of more than one species that could be in some way linked to the presence of life is something that we are looking for. We are looking for biosignature pairs, or even more. In this case, this is known as the triple fingerprint of water, ozone, and CO2 in the spectrum of the Earth. There is obviously, as I was saying, a chance of false positives, because some species may be produced by processes that are not related to life. That could be, for instance, volcanism. So ultimately, there will never be a way that we could tell we have found life on a planet. We will have always some sort of probability of finding life on a planet in this sense. Also worth mentioning other kinds of biosignatures, the surface and the temporal biosignatures. The surface biosignature on Earth is the so-called, the most known is the so-called vegetation red edge, which is the reflection of the plants, the green color of the plants, if you will, that are on the surface. And the temporal biosignatures, which could be seasonal variations that happens on Earth, for instance, with ozone that has a cycle and varies in abundance. Both these kinds of biosignatures are much harder to detect, especially when it comes to detecting an Earth-like planet, which will require many, many days of integration. So it's probably not really achievable at this moment. But the most important and the most famous biosignature pair is oxygen and methane. These two species are very important, and they are both present in the atmosphere of the Earth. And yet they shouldn't be, because the oxygen and methane react with each other very quickly. So it's very unlikely to see either of these species if there isn't a constant source of both these species. And in this case, the source of these species is life itself. So let's try and picture this as the pizza analogy, let's say. Let's imagine we are in a room full of grad students. If you see pizza on the table in this room, that means that they just brought pizza, because otherwise there is no way there's still gonna be pizza in a room full of grad students. And that's similarly to what this is basically what happens with oxygen and methane. If you see oxygen or ozone and methane together, that means that there is a constant resupply of these two species, and that's pretty convincing because it has no false positive. That would mean that this would be a sign of life. Okay, Sorry. Okay, so now we are ready to talk about the future missions and what specifically I am working on. We've seen so far the either the past, present, and future missions. They have been focused on building up a sample to do statistics on. And now that we have a large sample, we're starting to work more towards the characterization of the atmosphere of these planets. Eventually, we will push towards larger missions, because we will need to get to be able to detect smaller and smaller signals. And this is really important when it comes to detecting terrestrial planets, and in particular, habitable ones, or even inhabited ones. So let's imagine we detect an Earth-like planet. This is a picture that Cassini took. This is like, in a way, the pale blue dot 2.0. And this is the Earth. So from the distance of Saturn, we have looked at our Earth. And if we were to take a spectrum of this, to grab a spectrum of this in all wavelengths, we would see a variety of features that are interesting. In particular, in the top section, we see the reflected portion of the spectrum. That means that this is the light that comes from the sun and gets reflected by the Earth, either by the surface or by the clouds or the atmosphere itself. And this is interesting because it allows us to have many signatures of all the water, oxygen, ozone, CO2, but also this is the vegetation red edge that I was talking about earlier, and also the scattering caused by the atmosphere or the clouds. And this happens in the visible and near infrared. But if we push towards the mid-infrared, we see the thermal emission of the Earth. So the radiation that the Earth produces purely by the fact that it has a temperature. And we see also many other signatures that could be of interest. And both these spectral range have got the attention of the latest publications in terms of the Decado for the NASA side, or the ESA Voyage white paper, to try and trace and come up with a roadmap of what comes next. And this is in some way the roadmap that we should expect. After we are talking about 2030s, it's even a little bit optimistic in my opinion, maybe even more. We're talking about, let's say, a couple of decades from now. Both NASA and Europe we are both coming up with different concepts. In particular, the NASA-led one would be either LUVOIR or HABEX. They are most likely LUVOIR these days, but these are very likely going to be the next observatories focusing, and they will focus on the reflected light, so UV, optical, and near infrared, while the Earth, the ESA would look on, Europe would look for an interferometer that will look at the thermal emission of the atmosphere of the Earth. For me and for us, this would be LIFE, the large interferometer for exoplanets, and we will try to talk a little bit more in detail about this. So for reference, LUVOIR and HABEX would focus on the reflected portion of the spectrum, and LIFE would focus on the emitted part of the spectrum. So LIFE is a concept that looks like an interferometer made of 4 aperture telescopes and a recombiner telescope. They're going to be launched to L2, and the requirement is to do nulling interferometry and to detect planets that look like Earth, and then characterize them. So the focus here is between 0.5 and 1.5 Earth radii, and receiving between 0.35 and 1.7 times the insolation of the Earth. So we're talking about terrestrial planets. And the focus here is for the search of life, as the name would say. If you want to have a look at what we have done so far, I put here a few references to the paper that either have come out or are going to be published soon. And for the rest of this talk, I will quickly mention what I have done about this. And in particular, I focused on Life Paper 3, which has been recently published, and Life Paper 5, which I'm about to submit. And both these two papers work with the concept of atmospheric retrievals. Basically, we use a theoretical approach to understand what would be the best model to reproduce the data. This is useful now, even when we don't have the data yet, because we can use simulated data to both validate our routine, so validate the analysis pipeline, and also to determine the technical requirements for this mission. Because obviously we would like to create something that is actually going to observe what we want to observe. And it would be a little too late to know what would be the optimal layout if we launch it beforehand. So what we do is starting from the spectra and from the data, getting back to the theory in a way. This is what the retrieval module does. So let's try to quickly explain it. This is the spectrum. In this case, we have simulated a spectrum of the Earth, and we have created a noise. We have simulated a noise for each life point, trying to simulate an observation that would have been done through life. Then we use the retrieval framework, which is composed by a forward model, which is a model that can actively produce spectra, and then a parameter estimation routine. And what happens in this black box, in a way, is that we randomly draw sets of parameters and we make models with them. And then we compare the differences from the model and the data. Now, obviously, at the beginning, that will be totally random. So the model is very unlikely to look like the data. But learning and repeating the process more and more into detail, we get to eventually to a set of parameters that best represent the data. So we get a probability for each parameter, the so-called posterior of each parameter, to reproduce the data. And the parameters that we were working with are the surface temperature, the mass, the PT profile, so the thermal structure of the atmosphere, and the atmospheric composition of the atmosphere. And this is what was done in Life Paper 3 by a student of mine. And what we did was basically simulating the spectrum of the Earth, a theoretical spectrum of the Earth for now. And then we ran it through LifeSim, which is the simulator, the noise simulator for life that takes into account planet photon noise, stellar leakage, local and exozodiacal dust. So we tried to simulate an observation done with life. We produced these spectra at various resolution, wavelength range, and signal to noise ratios, because we are interested in knowing what would be the minimum requirements in terms of resolution, signal to noise ratio, and wavelength range for life in order to detect the major biosignatures. And then we apply the retrieval framework, which, as I said, goes from the spectrum to the data, to the parameters, to the models. This retrieval framework is very simplified for now, because at this stage, we didn't include clouds, and we didn't even consider a non-uniform distribution of the atmosphere, of the atmospheric composition. However, this was still a good and a valid work to determine the minimum requirements for life, as we will see here. So these are the results for the range 3 to 20 micron, optimized for short wavelengths, which is a particular baseline for life, and various values of SNR and resolution for all the major absorbers in the atmosphere. And the colors correspond to these classifications of the posteriors. Namely, if we get a red unconstrained posterior, that means we have absolutely no idea of how much of this particular component is in the atmosphere. If we get a green one, it's that parameter, that abundance is constrained. That's what we would like to have if we are characterizing the atmosphere that way. And these two middle situations are somewhat upper limits to the abundance of the various species. And from this plot, we see that for CO2, O3, and H2O, so the triple fingerprint, life is doing totally fine in detecting it. All of these species, no matter the SNR and the resolution. What we see is that we're not sensitive to CO, and likewise, we're not sensitive to N2 and O2 that we don't show for clarity. We only have an upper limit on N2O, which is a shame because it's also a very interesting biosignature. But what's interesting here is the methane, because methane, really, the detection of methane really depends on the SNR and resolution. So from this, we can establish what would be the minimum requirements for life, at least to detect, to some extent, CH4. And we identified that for this set of mirrors, 4 mirrors of 2 meters, each one 2 meter large, we need a wavelength range of at least 4 to 18.5 micron to detect most of the lines from methane, and a spectral resolution of 50 and a signal-to noise ratio of 10. These are the minimum requirements that we want to have. And this was validated on an Earth-like planet, a terrestrial planet. Okay, thank you. So the last thing that I'm going to talk about is the my paper, the one that I'm writing right now. So right now we have validated the pipeline, and we found the minimum requirements only on a modern Earth. But Earth has been habitable for, give or take, 4 billion years. So as we see here, it has also changed in time. The composition of the atmosphere has also changed in time. And in most of this, in this plot here, life has been present on the Earth. As we see here, these are in this area here, we still don't have a massive presence of life, still debated on that, but there is a fairly good agreement that at higher than 3.8 gigayears ago, there shouldn't be life on the surface. But when it started appearing, there were microscopic life consuming CO2, and then at the later stage generating methane, and here we see a bump in the composition of methane, and then at this point we get the appearance of bacteria doing photosynthesis, which accrete on the surface and then start being more and more abundant, so much that there has been a great oxygenation event around 2.4 billion years ago that has made a huge bump in the oxygen abundance, followed by another bump here in the Neoproterozoic, the so-called Neoproterozoic oxygenation event around 0.8 gigayears ago. And only then we get to the modern Earth. All of these scenarios are equally habitable and inhabited. So they're worth studying as well. So this is what I did in my paper. And we took into account these 4 epochs that I showed. So the prebiotic, the great oxygenation event, the Neoproterozoic oxygenation event, and the modern Earth. And we tried to see if the requirements determined by the previous paper still worked. And these are the results that we get. These are the PT profiles, so the thermal structure of all the atmospheres for both clear models and cloudy models. Our routine, I remember, I recall, doesn't include clouds. So in this case, we are not totally exact in retrieving a cloudy model. And this is interesting in terms of habitability. We're particularly interested in knowing what's the situation at the surface, and in particular to understand if the temperature at the surface is temperate enough to allow potentially liquid water on the surface. But what's interesting is that if we look at the chemical abundance, we see not a huge difference in terms of composition between the cloudy models and the clear models. This is a huge improvement with respect to the visible portion of the spectrum, so the reflective part of the spectrum, for which, if there are clouds, you won't see much of the abundances of the chemical species in the atmosphere. And zooming into this plot, the three more interesting molecules that could be potentially used by life to detect to have an idea of the presence of life on an exoplanet are obviously ozone, methane, and as we see before, not so much in terms of N2O, but O3 and CH4 are very promising candidates to determine in which phase of the evolution of the Earth we are. So not only we would be able to determine if the planet has life or not, but also at what stage of the evolution that would be. Now, granted, that's still a probability estimate, and we still will need to run this result into Bayesian frameworks that will allow us to determine what's the actual meaning of the detection we get in terms of biology and astrobiology. So to conclude, the takeaways of this last paper is that the requirements that we determined so far still work, and that there is a huge potential to differentiate between prebiotic and biotic worlds, in particular, trying to have an idea on the presence of biosignatures, such as methane and ozone. We can also constrain surface temperature, and clouds are not that impactful in terms of a characterization of the atmosphere, which is also a pretty cool thing. Ultimately, we would like to have both sets of data and to try and merge and get retrievals of both visible data and infrared data and see what else we can get from there. So I leave you with the summary, and we had talked about exoplanetology and the search for the habitable world as potential next milestone, and life in this context, life the mission as in this context, and what improvement it could bring to the whole idea of if we will find eventually an answer to the questions of life in the universe and everything. And yeah, I'll leave you with this. If you want to join the consortium, the initiative, feel free to do so. Check our webpage or get the newsletter. And yeah, that's it. I thank you all.
Thank you very much, Eleonora, for this interesting talk. If you have any question, please raise your hand or write in the chat. In the meantime, I would like to make you a generic question that we used to do at the end of this talk. Sure. Have you, for example, have you had any female scientific role models along your career?
Well, yes, I've had many, but if I have to think of one, I would say Margherita Hack, which she was a super famous Italian astronomer, and she was very much involved in outreach as well. And I read many of her books, and that got me really interested in the topic, no doubt.
That's since there are no questions yet, that connect to the next another curiosity. I know that you spent part of your life also writing in a column of outreach about forgotten female scientists, I think. So could you tell us something about this column?
Sure. So yeah, I am part of a Facebook page and also Instagram page to try and do scientific dissemination in Italian, and in particular in a dialect, in a particular accent, if you will. And every Thursday we talk about a forgotten female scientist, and it's very cool because you see all these people in the background. We actually talk about all of them, and I'm very proud to show it as our virtual background, no doubt. And if you want to have a look, or at least the Italian-speaking part of the audience, have a look at the column Giovedì Gnocche at La Scienza Coatta, the Facebook page. Yeah.
Maybe you can put, I don't know, maybe the link in the chat if someone is interested to check that.
Sure, I will. Now, granted, that it's very hilarious. It's not to be taken seriously because we use the laughter and we use irony to make science stick in a way, to do outreach. So it's very, very uplifting, especially in these days. Maybe that's what we need.
Yeah, exactly. Maybe this is what we say. Mm-hmm. So I don't see yet.
Let's see. Yep.
I think. No, there are no questions. I have a question by myself. Taking account, I am not working on exoplanets, so this could be a really dummy question. I mean, you said before that you make all this simulation with life, for life, taking into account a distribution, kind of homogeneous distribution of the atmosphere, right? Or
yeah.
How can it change, or how can you change the simulation thinking on something not homogeneous? I mean, it's not clear for me.
Right. So the problem here is that the Bayesian retrieval routines have an issue, is that they have somewhat of a cap in the amount of parameters that you can use in a normal amount of computing time. So there is some sort of a cap in like 20 parameters that you can use to make the simulation run and not take forever, right? So to simulate a varying a profile that's varying in altitude of a particular species, you would need more than one parameter for that. And so we are somewhat struggling to do that at the moment. But there are a few other ideas that would potentially allow us to reduce the amount of parameters by looking at them in a more clever way. And that would involve machine learning. And we are also working on that. So potentially this issue will be solved with the use of machine learning.
Yeah, but I mean, what do you understand but not homogeneous atmosphere? It's the most curiosity. I say I know our only point of reference, like you say, is Earth.
So it doesn't really matter as much for most molecules, but at least for Earth, we have a couple that do matter a lot, and it's water, because we have a lot of water in the troposphere, and then the stratosphere and the upper layers of the atmosphere are basically dry. So at that point, what kind of water signal are you detecting on a spectrum of? And at the same time, we also have ozone, since we don't have ozone in the troposphere, but we have a lot of an ozone layer in the stratosphere. And likewise, we're not sure on an exoplanet how that will behave. And so what we can do for now is just take some sort of average. It's a weighted average based on the depth of the atmosphere. So the deeper layer of the atmosphere matter most. And that's somewhat sensible in terms of...
And when you speak about clouds, do you understand cloud like the one that we understand here, right? I mean,
there are different kinds of clouds. Yes, we started implementing the water and ice clouds, the ones that we have here. But as soon as you start looking at other forms of clouds, like Venus, for instance, you need to take into account different compositions, of course, and that's very complicated, and people still are discussing how to best implement clouds in these cases. Yeah.
Yeah, that is what I was thinking. I mean, since I am not in the field, I say again, like you say, I think by clouds, something like the thing that I am seeing right now, but maybe in other planets, this is not like this. So how can you simulate that? It's really hard. I think it's really difficult to figure out how you can do this, from my point of view, at least.
Right, and also when he thank you, Serena, for the link. The thing is, also, as you were saying, the partial coverage, the cloud partial coverage rather than a cloud deck are modeled differently. And how do you exactly model that? We are still not sure. So yeah,
this kind of hard, I think.
Yeah, it is. I leave this to my student. He's handling this for the moment.
Not good thing, Drana. Okay, right. So
okay.
There are more questions. I don't see anything.
I have a comment, a question, a short one, but because it's since for life on Earth, phosphorus is very, very important. There are ways to find this one also in outer planets, or is very difficult?
So, I mean, phosphorus by itself, I'm not so sure, but one thing we are also looking for is phosphine. So this has been a huge deal lately for Venus, and we're trying to see if life would be able to detect phosphine on an Earth-like planet, or a Venus-like planet, or rather than a hot Jupiter or a Jupiter planet. Obviously, phosphine cannot be a biosignature depending on other condition. But phosphorus by itself, I'm not sure. I'm not sure we would be able to do that. But I think phosphine is a good track, is a good trace element for that.
Thanks.
Yeah.
Okay, so thanks again. So we close today's seminar now, and thank you to all for your attention. Please remember that you can find information about our program and speakers in the webpage of Laura Bassi series, and nothing else. Thank you for this clear and wonderful talk, Eleonora. Thank you very much.
You're welcome. You're welcome. Bye.
Bye.